see that fine? Can everyone hear me? Thanks. Today we're going to talk a little bit about asynchronous programming in Python. My name is Vic Kumar. So first of all, I want to get a show of hands. How many people here are using Python 3? And keep your hands up. 3.2 or higher. 3.5 or higher. 3.6. 3.7. And how many people have played around with Asyncio in Python? Okay, good. So in this talk, we're going to talk a little bit about what asynchronous programming is, what kind of problems it solves. We'll go over some basic definitions and terms. We'll look at what we already have in the ecosystem to deal with concurrent programming and why we need Asyncio. We'll look at the syntax of Asyncio as well as a few examples. And lastly, we will go over a few frameworks and how they've incorporated Asyncio into those frameworks, mainly web API-based frameworks. So first of all, I want to thank, I'm a software engineer at Excel. I want to thank Upside for hosting, Mike Brown and the other coordinators of Django District for giving me an opportunity here. I'm also a programmer, so I like a lot of different programming languages. My favorites are Python, Scala, and Go. I have a Twitter page, which is an accomplishment. And I also have a Bitbucket page over here, which has a repository called Python Async Await. And this has all the examples that we're going to go over during this talk, as well as a link to the Google Slides. So just up there on my Bitbucket page. It's not full screen. Let's try that. And we're back. Okay. So what is the problem that asynchronous programming is trying to solve? I always try to describe this using an analogy to one of my favorite games, chess. I don't know if they still do this anymore, but what they used to do is you would have a very good chess player, international master or grandmaster, and they would play exhibition games where they would play like maybe 24 people at a time. And you could observe that it would take the grandmaster about 5 seconds for him to move, it would take about 55 seconds for his opponent to move, and the games on average would take about 30 moves. So if we were going to do that, if he were to do that, he or she, as a sequential operation of events, take him 5 seconds to move, 55 seconds for his opponent, 1 minute per move, 30 moves in a game, and he has to play 24 people. So it would take him 12 hours. But that's not what he actually does in real life. The Grandmaster will go to one board, he will make his move in 5 seconds, and he will not wait for his opponent. He will go to the next board, move again in 5 seconds, next board, move again in 5 seconds. So he goes through all 24 boards in 2 minutes and 30 moves in a game. So he plays the same 24 people and wins all these games in 1 hour, not 12. So that's kind of like what we're trying to do with asynchronous programming. A lot of people will ask the question, does asynchronous programming make my code faster? It's like, well, not really. You can't make a DB call faster. You can't make this RESTful operation that fetches data from the internet faster. But what you can do is you can do more things at once. And so that's what we're trying to solve. It's a little difficult to reason about at first, but it allows us to handle more work with less resources. So that's why we have Asyncio in Python 3. We're going to go over a few basic terms and definitions. This is a very overview of like some terms that you're going to hear throughout the presentation, as well as with asynchronous programming. The first term is CPU versus I/O. So I'll just posit a question. How many operations can a CPU do at a time? This is
billions.
One. That's right. So the whole computer is like a trick. You think that a computer can do many things at a time, but in reality, the brain of a computer, the central processing unit, does one thing at a time. But the clock speed is and mine. I'm not going to minimize it, but mine is at 2.6 gigahertz. So that means it can do about 2.6 billion operations in a second and cycle between different operations, giving you the illusion that it does more things at once, more than one thing at a time, I should say. And if we look at like the architecture of how a CPU works, there's a CPU. The CPU has RAM, and it can do calculations, can do operations, But anytime you have to reach out to a peripheral device, there's an interrupt on the CPU. It reaches out across the bus, and then it deals with an external system. It gets the, so let's just say you need to fetch data from the internet. There's going to be an interrupt on your CPU. It goes across the bus to your network card and says, okay, get me data from google.com. You get some data back. The data goes back across the bus, and the CPU can continue handling that data. So when we look at this and think about the types of operations that we have, we can categorize them as CPU-bound and I/O-bound. Obviously, I/O-bound operations take a little bit longer than CPU-bound operations. So the whole problem that we're thinking about here with concurrency can really be viewed as an optimization problem. How can I optimize the number of clock cycles that are CPU-bound, and how can I minimize the number of operations which are I/O-bound? And so other examples of peripheral devices are like memory. I need to fetch a large file from disk. That has to go across the bus. I have to do network access. That has to go across the bus. I have to communicate with the database. That's an I/O operation. So these are just a few examples that you'll see of I/O-bound operations versus CPU operations. Do we have any questions on that so far? Okay, good. The second thing that we're going to talk about is synchronous versus asynchronous. And a synchronous operation is one where the tasks are executed one after another. In asynchronous operation, one task can start and complete independently of another task. And normally, asynchronous operations yield a result which will be complete at some point in the future. It's like a promise, a deferred result. There's a lot of terms for this. And normally, asynchronous operations are non-blocking, and they also often run in the background. One key observation that we can make is that the real world is in fact asynchronous. We write code that works with the real world, and the real world is events that do not happen one after another. An example of this would be that perhaps you have to call the phone company, and then afterward I have to send an email to marketing and tell them how this presentation went. So if I were going to do that in a synchronous manner, I would, when I call the phone company, obviously the first thing that's going to happen is I'm going to be put on hold for about 5 to 10 minutes. So the first thing that I can do, I can call the phone company, wait, be put on hold, talk to the guy from the phone company, and then go back and write my email. But if I was a little bit smarter about this, while the phone company is putting me on hold, I could write the email, or at least start writing the email, and then, okay, I'm off hold, I talk to the guy, I go back, and now I've finished the email. So I've kind of reduced the time. If I was really clever about it, what I could do is I could say, okay, I'll deal with the phone company and be put on hold, and Mike, I'm going to make you write the email to marketing. And that would be a really efficient use of my time, right? And so that yields to two terms which are very similar and often conflated. And those are concurrency versus parallelism. So concurrency just means that we can make progress on two things at the same time. And parallelism is in fact a type of concurrency, but it is dependent on the hardware, and that's a very important distinction. So if I only had one CPU, there's no way I can parallelize a task. I have to use that one CPU and split time across the CPU shares that I have, CPU cycles, I should say. So in our example with the phone company, when I was on hold and I started writing my email while being on hold, that's an example of concurrency. When I told Mike to go ahead and write the email for me, that's an example of parallelism. Do we have any questions on this so far? Okay, I guess we're moving right along. All right, so the second part is we're going to kind of take a look at what we already have, and these things have been around for years to kind of deal with concurrent programming. The first thing that we have is threads. So Python, as well as every other language that I know at least, has had threads for a very, very long time. Threads will let us run our operations concurrently, but because Python has a GIL, a global interpreter lock, threading does not provide true parallelism. Python has a separate module called the multiprocessing module, which is allows you to leverage multiple cores of your processor. And we're going to get to an example of this in just a second. But because I introduced the GIL here, the global interpreter lock, we're going to go ahead and talk about that for a sec. So The global interpreter lock is what ensures that the Python interpreter can only run one thread at a time, and it switches between those threads. When we talk about the GIL, we're really talking about the de facto implementation of Python, CPython. If we're talking about other implementations like Jython or IronPython, the GIL is not really applicable. And so even though the global interpreter lock, the GIL, gets a bad rap, a bad name, there's actually a lot of things that the GIL does very, very, very well. It makes single-threaded processes extremely fast, and IO-bound operations on this single thread have possibly, arguably, a marginal trade-off. The GIL also, and this is probably the most important feature of the GIL, is that it makes it very easy to integrate with non-thread safe C code. And this is one of the things that with Python, why we love Python, are these very powerful C extensions that we have where we can just wrap C code, make it safe, and run it very, very effectively, efficiently. So I think the GIL has a lot of positives. Not just, I know a lot of people, the GIL. So we'll go ahead and we will take a look at a very, very basic example of how threads work. Can everyone see that? Make it bigger, is what I'm hearing. Make it bigger. Is that bigger?
There we go.
That's good. Okay, so we have a program here, and we're going to import the threading library, which obviously this has been available since Python 2. This is nothing new. We're going to create a new worker, a threading.thread, and each worker has a number. It's just going to say, I am a worker. It's going to go to sleep for some random time between 1 and 7 seconds, and it's just going to wake up and say, I am a worker. I slept for this amount of time. So let's go ahead and run that example. Let me activate. Okay. Okay, so all the threads are queued. Okay, worker 4 woke up after 2. So we can see that we have threading and we can execute things concurrently. That's been around. There's nothing really new about that. Very simple example. Okay, switch back. And I don't know if I should full screen this. Okay, work. After threads, we have 2 other things, which are processes and concurrent.futures, which is new in Python 3. So processes, as we talked about a couple of slides ago, is from the multiprocessing library in Python. And this is what gives us parallelism in Python, where we can distribute a task across multiple cores. Anyone who's used the multiprocessing library in Python will notice immediately that it looks and feels almost exactly like the threading library. All the operations are very similar. I'm going to talk a little about concurrent futures, and then we'll do a couple examples on these. So the concurrent.futures library is new in Python 3. It's sort of like a wrapper around the processes and threading, where now we have a thread pool executor and a process pool executor. So we have a pool of threads, a pool of processes, and I can submit work to this pool, and I will receive a result that will be complete at some future time. A future object is returned. And I can check if this feature is done, and I can get the value from it when it is done. So let's go ahead and take a couple of very easy examples. So we saw the threading example here where I imported threading, and I created a thread by saying threading.thread. So if I look at the multiprocessing example, all I did was instead of import threading, I imported multiprocessing. Instead of threading.thread, I did a multiprocess.process. And basically everything else about my code is the same. And when I execute it, it's also going to run almost entirely the same, hopefully. Yep, so workers are waking up, and so that's it. We've executed these things concurrently. We will do one more example, which is our concurrent.futures example here. And so I have a function that is going to return after 3 seconds. I create a thread pool executor. I'm going to say, okay, let's schedule this function to run on my thread pool executor. On line 11, I'm immediately going to check if the feature is done. So the feature doesn't complete until after 3 seconds because it sleeps for 3 seconds and then prints out and then gives you a return of whatever you passed into it. In this case, hello is the message that we're passing in. So the first thing that it's going to check is, am I done? And it's not going to be done, it's going to be false. Then we're going to wait for 5 seconds. We're going to check again if it's done, and it will be done, and we're going to go ahead and get a result from that. So let's go ahead and see this very simple example of futures, concurrent.futures, which is in Python 3. So it's not done right now. After 5 seconds, it should be done. And then we got our result, hello. So you can see we have a pool of threads or processes. We can submit work to that, and we can get a future computation back from that. So again, here we can see, okay, we have some degree of concurrency already. Let's try that. Okay, so the summary of this is that you might ask, well, when do I use which library? And the answer to that question is it depends. It depends on what your program is actually doing. If your program is limited by CPU, like all your operations are CPU operations, you don't really have I/O operations, then if we distribute that work across multiple processors, then yeah, you're going to get some benefits. If you have a program where you're limited by I/O bound operations, but those I/O operations are relatively fast, and let's say you have a finite number of I/O connections available, then multi-threading can help. But in the real world, things expand, and I/O can become slower. You might want to make 3 requests, but suddenly now you have to make 10 or 15. So things grow. And so if the assumption becomes that, okay, my code is going to be I/O bound, but the number of I/O connections can expand and the I/O can become slower, then that is in fact where we need async I/O. Any questions thus far? You guys can butt in and jump in anytime. Okay, so async I/O is the new library that was introduced in Python 3 to handle these kind of things. And the first thing that we're going to talk about is that this actually puts Python on the same kind of playing field as a language like Scala or Golang, where we now see concurrency is a first-class citizen of the language. In fact, all the concurrency mechanisms of these languages, when we look at them, so Scala uses an actor-based model of concurrency. Golang uses Go routines, where you can, yes?
Question, is actor model concurrency built into Scala? Or is
yes. There used to be multiple different actor models, and they took Akka as the de facto actor model as of Scala 2.10. Scala uses actors, and Go uses Go routines, and Go routines have a channel where you can pass messages between 2 different Go functions, Go routines, if you will. And now we have coroutines in Python, and we have the idea of an event loop. And what these all are, they stem from a seminal work by Tony Hoare. Tony Hoare is the inventor of quicksort. If you've ever taken a computer science class, you're going to have to learn quicksort. He invented that. He also wrote a book in 1970-something, 78, 79, called Communicating Sequential Processes, which lays out algebraic formulation for how 2 processes can communicate with each other. And it turns out coroutines, Akka actors, coroutines, and the event loop are all types of communicating sequential processes. So they share that in terms of concurrency. So on the left, we see how we actually use async I/O. First thing we have to understand is what a coroutine is and how we create a coroutine. Coroutine is basically like a function, only we sort of decorate it. So there's 2 ways we can create a coroutine in async I/O. The first is by using the async keyword. So instead of creating just a function, def ping server, I say async def ping server. And the other way is to use the coroutine decorator, which is async io.coroutine. They're actually both exactly the same. They're equivalent. I like using the first way. I've seen other people who have preference for the second one. Yes?
I would like to point out that this first one won't work if you're not using Python 3.5.
Oh, good point. Okay, fair enough. That is, okay. I'm going to have to correct that next time I say I have this guy. Thank you. Right, so this is how you create a coroutine in Python 3.5 or above. And so what is a coroutine? A coroutine is kind of like a function, but when you call it, it doesn't actually run. It instead returns a coroutine object, which is essentially a promise, a future. It's something that's going to have a result later. And the only way that we can actually get a result from a coroutine is by scheduling it on this thing called the event loop, which we're going to talk about in like a slide or two. Async IO also comes with some very helpful functions. which can tell you whether a function is a coroutine or not, and that's called isCoroutine function. Also, we can evaluate the value of certain things in Python and check if they are coroutine objects from async.io. So we can tell from the return value if that is the return value from a coroutine or not. So I'm not going to spend a lot of time on this slide because this is the older syntax of Python 3.2. So this is how we used to do return a value from asynchronous routines. We would use the syntax is yield from, and it looks a lot like how you do generators in Python, where you just yield a regular value, but now we add the keyword from. And so you see we have an async coroutine, which is supposed to go get some JSON, and because load file is an IO operation, we're going to do yield from that so that we're saying this is going to be something that's going to be returned later. There will be a value. It's a future value. And you can only use the yield from inside of a coroutine. Otherwise, you're going to get an error like the one before where it says you can't use yield outside of a function. So that's important to know, that you can only use it inside of a coroutine, a Python coroutine. And so the new syntax is of Python 3.5 going forward is to use await. And so this is the async await syntax. It looks almost exactly the same. The only difference is instead of saying yield from, we use the word await. And much like yield from, you can only use await inside of a coroutine. And this is meant to be the proper syntax for Python 3.5 moving forward. If you do write Python 3.5, I believe all of them still support yield from right now, but eventually that's going to go away. Okay, so we talked a little bit about the event loop. And so you have a coroutine, but the coroutine doesn't do anything until you schedule it on the event loop. And what the event loop does is it tracks different, it's an IO switcher. It tracks different IO events. It switches to the ones that are ready, and then it pauses on the ones that are like kind of awaiting IO. And the result of that is you just don't end up spending time on tasks which aren't ready. Much like our chess example, what we're actually trying to do is just reduce the amount of time that we spend waiting. And so the idea is very simple. We'll move on to the next slide. And so over on the right, you can see a couple of the more detailed things that the event loop is capable of doing. Like it can cancel a routine, it can combine the results of multiple coroutines, create sub-processes, delegate function calls to a pool. And on the left, we kind of see a very simple example of how we might use the event loop. So we have an asynchronous function, a coroutine, which just says I print asynchronously. The first thing that we're going to do is we have to get the event loop, and that's done by async.io's.getEvent loop. And then we basically just run our function until it's complete, and then we close the loop. And that simple example is how you would just schedule the most basic function on an event loop. Do we have any questions thus far? Yeah.
So without the event loop, if you have a bunch of async.io like functions and stuff, nothing will happen.
You will
if
get
you like call them like it.
Yeah, you'll get like a coroutine object back from them. So it's like you'll have this future, but it never like executed. Yeah. I don't know if that's quite a suggestion.
Yeah.
And this toy example, this is just running one thing one time,
Yes.
asynchronously.
Yeah, right. It's not a very useful example. No, we're going to get to a couple more useful examples. And I use useful very liberally.
Just is it asynchronously though? Because if it's run until complete, right? Have you not
That's
made it
true.
asynchronous function? Just
I mean,
like it's
so-
gonna block on that call.
so in this example, this isn't even exactly IO bound operation, right? Like we don't actually even get anything by
Sure.
making it asynchronous.
Right.
But suppose that function was doing something else.
Right.
Which printing to a real printer.
Right. Then you might see some benefits, right? Because if we go back to like where was it? This slide, right? So this is CPU bound operation. We don't really care. Yeah, that is a good point. What slide was actually on this one?
Yep.
Oh yeah. So now we'll actually get to some real live examples. And as I said, so we did a couple of useless examples. Now we're going to do a useful one, which is that we're going to go get stuff from Reddit. So the first example that we're going to do, clear this out, is this guy. And this is how we would perhaps normally write it in a synchronous blocking fashion using Python's request library. So with Async IO, what we're going to see is that a lot of libraries don't take advantage yet of async IO. In the next section, we're going to take a look at some of the frameworks and how they use async IO. But what we'll see is that either a lot of libraries are making changes where they're taking all of their blocking IO code and switching it over to async IO, or you're going to see wholesale replacements to the library in question. And with requests, for example, in the async example, we cannot use requests. We have to use a new library called AO HTTP. So what we're seeing is a drop-in replacement for requests, which takes advantage of async IO. And so in this example, what's going to happen is we got 5 Reddits here. Funny, ask Reddit. Today I learned. I'm going to fetch some Reddits from this, and I'm going to print them out. Or I'm just going to get the results. And there's 2 things that I'm going to do here. I'm going to calculate the amount of time it takes me to make that HTTP request. So I'm going to go get this Reddit. It has some time. And I'm going to add up all those times. And I'm also going to print the time from when it started to when it ended. So before we look at any code, we're actually just going to look at these times real quick. So first, what did I just do? Did I change anything? No? All right. So here's the sync example. Okay. Got some Reddits, got some Reddits, got some Reddits. Okay, so the time that it spent cumulatively was 3.12 seconds, and the total time was also 3.12 seconds. Now let's just go ahead and run the async example. And what you'll notice is that the cumulative time is still 3 seconds, but the time that it spent from start till end was only 0.7 seconds. And that makes sense, because in the synchronous example, what it did was it said, okay, let's go to this URL, this HTTPS, get funny. I have to wait till that's done. Then I have to go get ask Reddit. I have to wait till that's done. Then I have to get the third one. In the async example, I said, okay, go get funny. Okay, I'm not doing anything. Just go ahead and get the next one. In fact, just go get all 5 of them at once. And when the last operation actually completes, just give me back all 5 results. It's in fact exactly like the chess analogy that we talked about at the beginning. We're just not waiting for stuff. And so you can see, like, yeah, I'll just run it a couple times. So sync example. 1, 2, 3, 4, 5. Okay, do it again. And you can see again, the cumulative time and the total time are very, very close. Okay, now let's run the async example. Done. Done. So just with like, and we're gonna look at the code here in a sec, but you'll see there's not a whole lot of changes with the code, and yet I perform these operations 4 to 5 times faster than I would just by doing one after the other after the other. And this is only with 5 Reddits. So now that I can get 5 Reddits, I want to get 10 Reddits. I want to get 20 Reddits. I want to get 100 Reddits. And when I do that, you're going to see that this disparity, we're not going to do it here, but you would, I would bet that this disparity will only increase. So the benefits you get from async IO right off the bat are really, really good. Okay, so let's take a look with the synchronous code here. So it's just a JSON.get on the URL, nothing really fancy. So we get the Reddits, we loop through R and Reddits and go fetch the JSON for that Reddit, right? Now we will take a look at the async IO. And the first noticeable difference here are the imports. So instead of requests, I had to use a library that makes HTTP requests asynchronously, AIO HTTP, something that returns a coroutine object, a future, right? And so we'll start again down here at the bottom. And so here you can see, I get the event loop. I do the same thing. I run until it's complete. And here I await and I gather a bunch of tasks. Each task is the result of an async function. So get Reddit in the other example was just a regular function. Here it's an asynchronous function. In fact, a bunch of them are asynchronous functions here. So all I really did was switch a couple of libraries around and use async IO. Do we have any questions with this? Okay. Full screen. Sorry. Okay, full screen, please. So now we can see that there's a couple of options with async IO. Either we have to go through our existing code base and take the blocking IO operations and sort of replace them with Python coroutines and take advantage of async IO, or what we see are drop-in replacements for things that already exist. So we're going to talk a little bit about the state of where we are with async IO in Python 3 and a couple of frameworks that I like and that you guys probably use. They're mainly going to be web API kind of frameworks here. The first one is Tornado. Let me get out of full screen mode here. So I just have a couple of like internet articles that kind of showcase the state of where things are. So this is a long post on essentially the history of how Tornado adapted to coroutine. So you had Tornado and Twisted are actually the closest, and they took advantage of it first because Tornado had an event loop, and Async IO introduced an event loop. So it was really just bridging a few things here and there. But originally they started with something like this. Instead of a coroutine, they had their own decorator called gen.coroutine.
Make that bigger, please.
Oh yeah, fine. Yeah, thanks, Mike. Is that good?
little
Bigger?
more.
A little more? Good? Bigger?
One more.
One more?
That'll do it.
Good? So you can see that they had a decorator to, so instead of async.coroutine, you use gen.coroutine, and that sort of bridges the gaps between Tornado's event loop and async IO's event loop. And this is already deprecated because he has a long look. He just goes on, and then finally he tells you, oh yeah, Tornado 5 already incorporates async IO. So if you're using Tornado 5, you're good. It's already there. And before that, before even all of this, I probably should have started with this, because this is how it started before. You had a module that bridges between the two right here. But this is also deprecated because, as I said, Tornado 5 uses async IO, and you get all the benefits of async IO using Tornado 5. So that framework, we have it. It's good. If I go back and I go a little down to my next slide, we have Flask. And so how many people here use Flask? Okay, that is good. And the answer to this, so I mean, if you use Flask, you're probably saying, hey, can I use async IO within Flask? And the answer is like, kind of, sort of. The views in Flask, they're still going to be synchronous, but you can do asynchronous stuff within that view. So, and this is going to be similar with Django, and we'll talk about like maybe some cases where you might want to use async IO from within your synchronous view. So here, I think there's some functionality, but there's also now a wholesale replacement for Flask called Court. And this has gotten a lot of popularity just in the last 8 months. So just like we saw with requests and AIO HTTP, we can use Flask, we can just drop in Court and use all the same things that we would use with Flask, except the views are already using async IO. So the views that you have in Flask are just regular functions. The views that you're going to have in Court are going to be coroutines. And you're going to get all the benefits and the features of that. Yes?
So, all the benefits and features of that. What's like some good examples of things that you, like new goodies that you have with using Court over?
Okay, so essentially every request is going to be something that executes asynchronously. So in a normal web app, you have like, I have a request, and then this request is tied up until I respond. So if I have a lot of users, and I only have a limited number of requests on my thread pool, which can answer users, then I could occupy all those threads because I'm using up those threads. But if I shift the work onto the event loop, then this thread is now free to go back and answer more requests while work is going on in the background. So with this, you would potentially be able to handle more requests, right?
Yeah.
So does that mean that with Court, when you do like a database request, for example, it is natively asynchronous? You don't have to do anything special?
Yes. So that's also it. The database. So database IO. It also depends. The request cycle is going to be asynchronous, so you will get that benefit. But the database, like the drivers that we use, like psychop-g or whatever, those are synchronous. And actually, what is it? Postgres. Async. There's a drop-in replacement for.
Async PG.
That's it. Async PG. Nice. Yes, that's what I was looking for. Yeah. So you could use async PG, and then you could have async on your request, and you could also have async with your database communication. So you would have async from top to bottom. So again, they're drop-in replacements for some of this stuff, and that was real awesome that you knew the library already. That's great. Good.
Is there, I guess you could probably even, probably some uses where you can like, say, take off, like right now it's like, sometimes I kick off things to celery, you know, because.
So celery is
Yeah.
a great, so yeah, you would need celery, because celery is actually doing some of the stuff for you, but you have this sort of queue in between, and then you have another process over here, right? So now the queue's kind of built in, and the process is just in the same sort of, what do you call it, like the same repository program. So yeah, Celery's not bad. I still think Celery has good use cases. If you want to distribute your sort of asynchronous mechanisms, then Celery is good, because Celery can be backed by like Redis and RabbitMQ and stuff like that. Okay, so the last one, or almost to the end, we have Django. And this is similar to Flask. So this guy sort of wraps a function, and then he starts an event loop. So you have a synchronous view, but you can do asynchronous stuff in the background. And I liked this post because it actually answers, like, what do you mean by doing asynchronous stuff in the background, right? Like, why would I ever do that? And, right, let's suppose you want to send bulk email. Okay, that's a great example where you could use async IO, right? Like, you have a synchronous web request, but in the meantime, I also have to email like 100 people. So then there, you might want to start a Celery task, but now I can just start an async IO task, and boom, I don't need Celery, I don't need this infrastructure in between me and the worker process, which is actually going to send out the bulk emails. You can take the same example, I can do bulk updates on multiple records in the database. Okay, so you just start this sort of asynchronous coroutine from your synchronous code, and that just continues executing in the background. And meanwhile, you're free to go ahead and respond, give your user back their JSON or their web template, whatever have you. So that's what we kind of mean by, like, we can use async IO even within the bounds of a synchronous framework. I could press escape.
For reference, Celery is roadmapped with 5.0 to use async IO, right? So Celery serves a bigger purpose than just running sub-processes. So I wouldn't diminish it too far. But to your point, yeah, if you're just trying to do something simple,
No, I think like,
or you're just writing like you need an asynchronous task done, you don't need to go outside of something like Celery for such a small lift as running something asynchronous.
I think distributed is
Yeah.
where I really think Celery has a lot of benefits, right? When we want to distribute that, then obviously, I love Celery. I love Python. Okay, so we have all these examples, and we're going to do one final example, and we're going to take a look at a small piece of Django, excuse me, which is Django channels. So Django channels is the WebSocket framework for Django, and WebSockets is actually it's kind of unique to take advantage of async IO because it's sort of an event-driven, message-driven architecture already. And Django channels, just like we saw with Tornado, it's async IO completely ready to go at this point with Django channels 2. So we're going to go ahead and take a look at an example. Actually, let's just go ahead and run my example. Oh, none of you guys have your computers? Okay, so within here, I have a Django project, which I misspelled with Reddit reader, that's what it's called. Okay, and I can do a Docker compose up on this. And in the meantime, I'm gonna get another terminal up, right? And we'll do ngrok on this. Oh, right. Ngrok HTTP 8000 would work. Okay, so if you do have your computer, you can now visit this at this sort of gobbledygook URL, if you can see it. And this is actually the same example that we had before. I'm going to bring it up here on my local host. And so this just searches Reddit using async IO. So like, let's say Python programming. And I hit search. and I'll go ahead, find the Reddits, and then go ahead and display them. Let's find like jokes about Trump or something. And so here we go. We got the Reddit information that came from those 2 subreddits. And we're gonna go ahead and take a look at the code for that. Where was Visual Studio VS Code? There we go. Right, so when we start with the Reddit reader, the main crux of it is the consumer. So we send this message and the consumer is what asynchronously picks it up and handles this. It's what looks up the Reddits for us, right? So what we notice is that from Django channels, we import this class called async HTTP consumer, which is built in. I create a class which inherits from async HTTP consumer. I go down and there's a special function here called handle, which is decorated with the async keyword here. So we can see that it is a async coroutine in Python. And this code is actually very similar to the previous example we did. I literally just moved large chunks of it into here and it just works. So I get an event loop. I create like a task. I gather these tasks together to get one sort of computation from several concurrent results. And then after all that is done, I asynchronously send a response back on the socket. So I get a message from the socket, I do these Reddit feeds, and then I send back some JSON. And in fact, we can, I believe you can see that in the console. Right. So I got these as responses. So you have jokes, you have Trump, and so forth. So this is the Django channel part of it. So you have a consumer, you have a route to that consumer where you set up a router for Django channels to route to your consumer. And then on the front end side, if I go to my templates and I just go to my index, it's really just a little bit of JavaScript here where I make an AJAX request to that WebSocket, and when it's done, I have a callback to go ahead and display that information on the page. Do you have any sort of questions?
Have you done anything with map and reduce with async loading?
I have not.
That'd be an interesting application for like data analysis type.
You don't want to do data analysis asynchronously.
No, yeah, sure. let me not talk about it too much, but a good application for it. Right?
And so I honestly thought that you guys would have like a lot more questions. But that's really all that I have about async IO. That's all.
One other quick question. In terms of the channels example there, you're talking about, what was it?
Static.
No, the async.
Async PG.
PG. Does that have a integration with Django yet in terms of the
I don't. So AIOPG is an asynchronous module to communicate with Postgres.
Right.
Right. That's the module we're talking about.
Yeah. Async PG.
Right. So that if it were to integrate with Django, it would work within the Django models framework.
Right.
I do not think right now, as far as I'm aware, that that's integrated. Of course, you don't actually have to use Django's ORM at all.
Right.
You could use something like SQL. See, I know AIOPG works with SQL Alchemy, for example.
Doesn't
So
work
you
with
could.
the ORM though.
Huh?
Doesn't work with the ORM.
SQL Alchemy's ORM?
Yeah, it doesn't work with the ORM. It only works with the query builder.
Oh, the query builder. Okay.
So like
okay.
so like the SQL Alchemy team has actually said they're not going to support like async stuff because it would require like a lot of what Vince is saying, a lot of reworking of the ORM unit of work method. I imagine Django's ORM has a similar.
Yes.
Yeah, I think I wasn't there for the PyCon recently, but Andrew Godwin, the guy who writes.
And Django channels and South migrations.
That's right. Yeah, he's could have sworn the last like update of everything he was talking about how they want to move Django's ORM to an async model. Like this is like a not anytime soon thing, but like slowly moving towards it thing. I could be wrong about that. Though.
So on that note, like that's actually why I wanted to talk about the frameworks because I've seen like a lot of them looking for contributors, like open source contributors, and like it's actually like a very exciting time in the Python community that a lot of these libraries are trying to move over to async IO, and they're looking for people to help out and make these kind of changes.
Yeah, I didn't realize that Flask was already.
They're all in some.
dipping their toes
Yeah, that's
in
what's
some-
interesting. They're
yeah,
all in
yeah.
some like Some of them are already done. Some are in some kind of in-between state. So it's almost like every couple of months you check in. It's like, oh wow, they made a lot of progress on this. You know.
So somebody's been taking a closer look at this than most of us in the room. Like, do you feel like 5 years from now you can see a big shift towards this kind of model?
This is the way it's going to go. Async IO is here to stay, and I think like you'll see either one of two things. You'll see either the wholesale replacement, like Core to Flask and AIO to HP, or eventually they'll get there with. I mean, they'll get there.
Microservice architecture is going to drive it there too, right? Because everything's a service, and so you're not going to have monolithic applications anymore. You're going to have service brokers where you have to wait for that response. So every service broker will be talking to every other service broker asynchronously, right?
Okay.
Cool.
Everything I had.
All right.